So a little over a month ago, I had the
Brilliant.
idea of creating my own operative system. It's actually a project that I've wanted to start since I was in college, which is where I learned that I was interested in low-level programming. But that never really went anywhere. The furthest I ever got was on a Raspberry Pi. I was able to turn on an LED. Really, it was supposed to blink, but even that was too much for me back then, so I just abandoned the project and moved on until now. This time, I decided that I want to do things properly, and so I created the redacted operative system. I'm not being secretive here, I literally just couldn't come up with a good name for it, so I just called it redacted. This time, instead of trying to run directly on a Raspberry Pi, I decided to run it on QEMU instead. Yeah, wait, that's not it. That's it. That's pretty much the same thing. So before we start, I'm just going to give you a disclaimer. I am going to try to explain things to the best of my ability in a way that pretty much anyone who's watching this video can understand, but I do suggest that you at the very least understand a little bit about low-level computer programming and about computer architecture. Though if you don't, I really don't know why you would have clicked on this video, but hey, if you have, you're welcome to stay. Let's talk about what is an operative system in the first place. So an operative system is a system that operates the computer. Yeah, that's pretty self-explanatory to be honest, but honestly, that's actually what it does. It's responsible for booting the computer, presenting an interface to the user,
reading the user's
installing backdoors for the FBI memory, installing backdoors for the CIA, stealing your data. Okay, enough. So yeah, just a lot of things. Now, this is definitely just a hobby project that I'm doing just for fun because somehow this is my definition of fun. But even then, I will still need to do most of the things that I mentioned if I want to go anywhere with this project. So let's get started. The initial steps for this were surprisingly the easiest. Turns out there's actually plenty of tutorials for setting up a little Hello World project on QEMU for the ARM architecture, which is what the Raspberry Pi uses, although most of them did not rely on Raspberry Pi, so I abandoned that part for now. Most of them essentially rely on making your operative system talk to a UART device, which is essentially a type of serial device, just a device for very simple input and output. Now, normally, if we're running this on real hardware, we don't really have a way to know what our output is unless we hook up a device to our serial output. But since we're working in QEMU, it's actually trivially easy to just connect it to our computer's terminal and see it there. All that to say, my operative system just prints Hello World to the computer's console. Now, before we continue, let's talk a little bit about languages. My operative system is largely written in C. Even though I did end up writing some parts in C++ eventually, and some parts of the operative system are better off written in assembly. Now, the thing about assembly is that this is a very low-level programming language. In fact, it can be directly encoded into computer-readable instructions. But because of that, it's actually really good at directly accessing memory. Now, C is a little bit higher level, but it's also really good at accessing memory, which is why we're also using it. And then there's C++. It's higher level, but it has plenty of quality of life features such as classes, inheritance, and all that nice stuff that us programmers are pretty much used to. So I do end up using it in some places. But most of the core is written in C, and the other things that are built on top of that may be written with C++. Now let's talk about our actual Hello World program. It starts with a boot.s file, and that's boot.s with a lowercase s, and this will come back to bite me in the ass eventually, but we'll get to that in another video. For the time being, all you need to know is called boot.s. The file looks something like this. Essentially, all it does is just load the stack from an address that we're going to define later on, and essentially the stack is just a piece of memory that is used to aid our program's execution. For example, local variables declared inside a function may be stored on the stack. After that, we just call a function called kernel.main that we're going to see next, and then it just loops indefinitely. So let's get to the kernel. The kernel is defined in a file called kernel.c, and that's where the kernel.main function is. Right now the function is just one line. It just calls this other put_uart function with a string hello world. So let's look at how that's implemented. We have our uart.c file. And essentially the way that our UART function works is it scans our string until it reaches the special terminator that we use to indicate that a string has ended. And as it does so, it writes it to a predetermined place in memory. In this case, it's this address right here. Now, let's talk a little bit about this address because it's written in hexadecimal. Now, when you and I do human math, we use the decimal system, essentially numbers from 0 through 9. But computers use the binary system, zeros and ones. So As a compromise between the two, we actually came up with a hexadecimal system that goes from 0 to 9 and A through F, representing a total of 16 digits. Very intuitive. Okay, jokes aside, it's actually incredibly intuitive for computer programming because, as it turns out, 1 digit of hexadecimal is the same as 4 digits of binary, which are also called bits. Let's take as an example the number 31. The number 31 in decimal is written as 31. In binary, it's written as 5 different ones, or 11111. In hexadecimal, it's written as 1F. And you'll notice that I used the 0B and 0X prefixes for binary and hexadecimal, just so we can tell these numbers apart. Okay, now that we've clarified hexadecimal numbers, let's move on to the linker. So far, we've written 3 different source files, the kernel, UART, and boot. But these are separate, and we need some way of putting them together and compiling them into a single file that QEMU can then execute. To do that, we're going to use a linker. And to tell our linker how to link our program, we're going to define a linker file. It looks something like this. Essentially, it just defines the entry point to our program, which in this case is the start function that we find in the boot.s file. Then we declare where the program is going to start in the computer's memory. Then it loads the actual program and leaves aside 4 kilobytes of space for our stack, and then creates this stack top symbol that we saw before so that we can load it into the program from our boot.s file. Okay, so putting it all together with a makefile, we're going to take our source files and compile them with these commands. Then we're going to take our linker and join them all together along with our linker file with this command. And finally, we're going to use this last command to generate our .img file that QEMU is going to be able to execute. Okay, so let's run it. We're going to run it using this QEMU command. Essentially, we're just telling QEMU to emulate a versatile PB board with 256 megabytes of RAM, no graphics, and with the kernel that we just created. And if we run that, we get this, our hello world. Now, let's talk for a second about this running RPi emulator and about the versatile PB that I mentioned before. I mentioned that I wanted my project to run on Raspberry Pi, but for the time being, we're actually not relying on Raspberry Pi at all. We're instead relying on something called Versatile PB. This is a board provided by QEMU that we have designed our program for. There's just one tiny problem with this board. It's 32 bits. So let's talk about the difference between 32 and 64 bits. 32 and 64 bits actually just indicates how much data the CPU for our computer can process at once. With 32 bits, it can process 32 bits, and with 64, it can process 64. That was pretty easy to understand. But what this means in practice is that if we think about numbers, for example, we can represent values up to 4,294,967,295 with 32 bits. Or half of that if we use the last bit to represent the sign so we can have negative numbers. With 64 bits, we can have a lot more. In fact, we can have this number. I'm not going to attempt to read it, but I think it's actually something like 18 quintillion. So yeah, quite a lot more. This also affects other things such as, for example, how much RAM is available. On a 32-bit system, we have a total maximum of 4 gigabytes of RAM. On a 64-bit system, well, it's actually so much RAM that we don't have to worry about it for the foreseeable future. Now, we probably want to use 64 bits then, since this is the standard in the year 2025, but most of the resources that I found to get started were actually for 32 bits, and they were actually over 10 years old. But lucky for me, I found this GitHub repository, which is also 10 years old, which adapted the exact tutorial that I followed to get my hello world from 32 to 64 bits. Essentially, we're going to have to make a few minor changes. First off, we're going to swap out our Versatile PB for a VirtIO board, which is a more modern and 64-bit board. Because of that, we're then going to have to change the address for UART, and we're also going to change the address to which we are loading our memory. We're eventually going to have to change it again, but for the time being, this is where I was loading my operative system. Finally, we have to change the compiler that we're using to also be the 64-bit version. And with that, we get our hello world back, but this time in 64 bits. Amazing. So what now? Well, we're going to work with the GPU now. And you may be thinking, wait, you just did hello world, so now you're just going to jump directly to graphics? Aren't you skipping a bunch of stuff? And technically, yes, there is all this other stuff that I should be building that I can then use to build other things such as graphics. But the truth is, there's not really much of a point to building these things right now because there's nothing to use them. So that's why I decided to focus on the GPU instead. I'll be building these things along the way as I need them for the goal that I'm working towards, in this case, the GPU. So for the GPU, I decided to use the VirtIO GPU PCI device. As its name indicates, this is a virtual GPU. What that means essentially is that our operative system is going to be communicating with this GPU, and this GPU in turn is going to be communicating with the GPU for my operative system on my computer, and it's going to be using that to then render to the screen. And again, like its name indicates, this is a PCI device. So what's PCI? PCI is the protein C inhibitor. Wait, no, that's not it. Hold on. It's the Paralympic Committee of India. No, that's also not it. Hold on. Right, it's the Peripheral Component Interconnect. This is a bus standard that we can use for devices to communicate with the rest of the system. Now, all we need to do to get our GPU working is finding the GPU over PCI, enabling it, configuring it, and sending data to it. It's that simple. Just like that, we get graphics. Okay, it's a little bit more complicated than that, but this is a very high-level overview of how it works. Let's actually go into the implementation for it. So what we need for our GPU to work is a driver for it. Now, the driver is going to be specific for our GPU. If we ever want to support other GPUs, we're going to have to write other drivers for them. However, the code that we write for PCI is going to be the same for pretty much all of them. So let's actually get started on finding the device over PCI and figuring out how to use it. So how do we use PCI? Well, the way PCI works is essentially it's located at a predetermined place in memory, and it has a list of devices, which looks like this internally. What we need to do is we need to find the device that has the device ID and vendor ID that matches the one for our GPU. In this case, it's 0x1050 for the device ID and 0x1AF4 for the vendor ID. So we're just going to go through the devices until we find the one. Our next step after that is to ask the device how much memory it needs to be configured. The device will tell us what memory it needs, and we will allocate that memory somewhere where both our OS and the device know that it is located. So the proper way to do this is to read the capabilities pointer of the device on the PCI interface. This will tell us what capabilities the device has, essentially what it is capable of doing and what we need to do to configure it. In order to configure it, we'll need to access the base address register for each of the capabilities that we want to enable and use it to allocate some memory for it and tell it where that memory is. But for the time being, since this is just a proof of concept, we can just skip all that and hardcode it. For our GPU, we actually need to go to bar 4, so the fourth base address register. Once we're there, what do we do with it? We're supposed to write all 1s or all Fs if we're working with hexadecimal to the base address register, at which point we will read back the size that the device needs in order to write its configuration. And then our operative system is responsible for allocating some space and telling the device where that space is, but again, we're just going to hardcode it for now. So now we've told the GPU where we're going to be able to configure it, and now we have to actually do that. But how do we do that? Well, this very much varies per each GPU, but our VirtIO GPU has a spec that we can just read and figure out how to do it. It should be pretty trivial, but please do not underestimate my lack of attention to detail. So a very high-level overview of what we're supposed to do to initialize the device is it has a status register at offset 1.4 of the configuration space that we just indicated. There we have to write a 0 to reset the device. After we've reset the device, we have to acknowledge the device and tell it that we are going to be able to communicate with it. We do that by writing a 1 to the status. Then we need to tell the device that we know how to drive it. We do that by setting the status to 2. After that, we have to go to offset 4 of the device's configuration, and there we will read the features of the device. This is essentially where the device is going to tell us what it's capable of doing. We're supposed to read this, parse it, decide which features we are able to support in our driver, and then write it back to offset 0xc. However, for the time being, I'm not really parsing it or doing any of that. I'm just writing back the exact same features that it tells me and hoping that that's good enough. So far, it's worked. After we've done that, we inform the GPU that we have finished the negotiation of the features by setting an 8 to the status bit. And then we're supposed to read the status bit back. If we read anything other than 8, that means that the GPU has actually rejected our negotiation, and we probably need to start again because we did something wrong. But if everything went well, the next step is to set up virt queues. Now, I'll talk a little bit more about virt queues in a second, but all we need to know is they're places in memory that we're going to address to send commands to the GPU and tell it what to do. Before we talk about them though, let's talk about the last step. The last step for our GPU to be active is to tell it that our driver is okay and ready for the GPU to be active. We do that by writing a for to the status, at which point the GPU will actually be live and ready to receive our commands. But okay, let's actually talk about these vert queues for a second. Essentially, vert queues are going to be used for us to communicate with the GPU from now on. We are going to send commands to it, and it's going to write data back to us. Now, we are going to set up some place in memory for us to do that. We're going to write to it, and the GPU is going to read from it, interpret it, and do what we're telling it to do. However, to do that, we're going to have to decide where these vert queues sit in our memory. And to do that, we're going to need an allocator. So we want to keep it simple for our first allocator. And essentially what we're going to do is we're going to have some place in memory set aside to then give it out to whoever requests it. We are going to be keeping a pointer to this memory. And when someone requests memory by asking for a specific amount of memory, we're just going to give them the address that our pointer is currently pointing to, which is the next available address. And then we are going to increase our pointer by the amount that they have requested, indicating that that memory is now taken up by them. Now, this works fine for basic allocation of memory, but it has one major flaw. If memory ever becomes free, we have no way of tracking that and reusing it for something else. Essentially, there's no way to free memory. Now, for the purposes of our allocator right now, this is totally fine. After all, if our vert queues disappear for whatever reason, we probably have bigger issues than non-reusable memory. But eventually we will come back to this and revisit it and create a proper allocator. For the time being, let's go back to the GPU. So now we have our GPU when it's live, and our operative system now wants to tell it what to do. We're going to do that through commands. We're going to go through some of the most basic commands that we're going to be using, and pretty much the only ones that I have implemented so far. The first one of which is getDisplayInfo. This is probably the first command that we're going to want to send, and we're essentially asking the GPU to tell us what displays it is connected to and what their size is. So we're going to give this command to the GPU is going to search for displays and report back what those displays are and what their size is. Once we know we have a display, we're supposed to create a 2D resource. Now, it's not really important what this is, but essentially we're just telling the GPU to create something in its memory. We're going to give it an ID, in this case it's resource 1. We're going to give it a size, and then we're going to tell it what format the data is going to be in. In this case, we're going to use the B8, G8, R8, A8 format, which is a mouthful. Now, what does this actually mean? I assume we all know what pixels are, but just in case, we can think of pixels as 3 little lights, usually red, green, and blue, which we can light up to different intensities, and then our eyes will detect them as just one color. So our format from before, B8, G8, R8, A8, is essentially just telling the GPU how much data we're going to send for each of these channels and what order it's going to be in. In this case, we're telling the GPU that we're going to write 8 bits for blue, 8 bits for green, 8 bits for red, and 8 bits for alpha. Now, alpha is transparency, but for the time being, we're not going to deal with transparency, so I'm mostly going to ignore it from now on. Here's the interesting part, however. Even though our format is BGRA, we're actually going to be able to write hexadecimal to write colors in the ARGB format. Now, the reason for this is a thing that I really don't want to talk about, and it's endianness. For whatever reason, I really hate talking about it, but I guess I have to. Essentially, when we write this hexadecimal number to our memory, it gets written backwards as BGRA, and it perfectly matches the format that the GPU is expecting. Now, the reason for this is endianness. The least significant bit gets written first, and then as the other ones get written, they get written afterwards. So just like that, we're writing it essentially backwards. So long as we're writing hexadecimal, we can write it in the ARGB format. And actually, we can mostly skip the A because, like I said, alpha is not really relevant at this point. So let's see an example of this. Let's use this color, B4DD13. So again, the format is RGB. This means that B4 represents red. And if we translate this to decimal, it's 180 out of a maximum total value of 255. Then we have DD for green, which represents 221 out of a maximum total of 255. And finally, we have 13, which is actually 19 in decimal out of a possible 255. And then we have alpha, which, like I said, it's just 0. So what this means is a fair bit of red, a lot of green, and not a lot of blue. Or, as the kids are calling it nowadays, Brad Green. Great, now that we've talked about pixels and colors, let's go to the next command, attach backing. So you remember we created a resource in the last step, but what exactly is that resource and what are we going to do with it? Well, that resource is actually going to be our pixel data that we're going to write and then the GPU will render to the screen. But we haven't really defined where that is going to be sitting in memory. Where do we go to write it? Well, that's where the attach backing command comes in. First, we need to use our allocator to create a frame buffer, which is essentially just the memory that we're going to be writing our pixel data to. And then we send that to the GPU via this attach backing command. And the GPU will just keep in mind that this frame buffer corresponds to the resource. Now we get to our last command before we can actually start drawing to the screen. That is set scanout. Essentially, we're telling the GPU that the resource we created needs to be attached to the display that we detected in the first step. Great, so now our GPU is ready to render our data. But in order to do that, we actually have to talk about two more commands that we're going to send out whenever we have new data for the GPU to render. The first one of which is transfer to host. In transfer to host, we are going to write content to our frame buffer and then tell the GPU that we've updated the frame buffer, and the GPU will update the resource. And then we'll tell the GPU to flush. And this essentially just renders the resource onto the screen. Great, so do we have pixel data now? Actually, no. I ran into two major roadblocks that actually led me to abandoning VirtIO GPU for a little bit anyway. At the time of writing this video, I've actually gotten it to work, but by the time that I was doing all this, I actually abandoned it for a bit. The first of these roadblocks was with getDisplayInfo. This is the command that we give the GPU to tell it to find any displays and tell us their size. The problem is we weren't really reading back any data from it. So I started investigating a little bit, and from what I heard, apparently VirtIO GPU is not very compatible with macOS, which is the system that I was working from. Or at least that's what those threads said, but they were a couple years old, so just in case I checked and double-checked the spec, and everything looked fine. But it did say that if no display gets detected, we can just create one with a default size. So I decided to just do that and move forward. But immediately moving on from roadblock 1, I ran headfirst into roadblock 2. Roadblock 2 was a scanout error. Scanout is the command that tells the GPU that the resource is supposed to be attached to the display that we detected. Now, already it's a problem because we haven't really detected any displays, but even then it should technically work. The problem is we were reading back wrong resource ID. Essentially, the resource that we were addressing did not exist. Now, this would be fine if it wasn't for the fact that I was actually hard-coding the resource ID to always be 1. So this didn't really make sense. And again, I started investigating, so I checked and double-checked the spec and everything looked the same. Psst, guess what? It was not the same. And eventually went back to some old threads on Reddit talking about how VirtIO GPU is not really supported on macOS. So seeing these issues, I decided to just let go of VirtIO GPU for a bit and try to work with another GPU for a while until I fixed this or until QEMU eventually added better support for it. Before we move on though, I just want to clarify, the issue was entirely on my end. But okay, for the time being, I decided to move on from our VirtIO GPU to our next GPU, RAM-FB. As its name indicates, RAM-FB is a frame buffer in RAM. It really couldn't be simpler than that. It's a very, very simple GPU implementation. And compared to VirtIO GPU, it was definitely a breeze to implement, but even then it had a couple challenges. The first of these challenges is my QEMU binary that I was using actually does not have RAM-FB. So I needed to compile it from source so that I could have RAM-FB. The second issue is RAM-FB doesn't really exist in memory. Instead, to address it, we need to use something called the firmware configuration, which is something that QEMU provides to configure our firmware. Yeah, a lot of these names are pretty self-explanatory, honestly. So the firmware configuration works by setting up a bunch of files that we can read and write in order to configure the system as we're booting. Specifically, we're looking for a file called etc/RAM-FB. Now, in order to do that, we need to find the firmware configuration, which is hard-coded at a specific address. Once we have it, we need to read two offsets, the control and the data register. To know we're in the right place, we can find this value 55-4D-4551 in the data register. And if we want to translate that, that translates to QEMU. Wait, what? It's
flipping
Endianness again. Okay, so what do we actually do with this firmware config? Well, we send out a command to it. The command is 0x19, which stands for list directory. And from it, we're going to read a bunch of data that comes in this format right here. Essentially, we're going to read a file with a selector and a name. The name is what we're looking for. We're looking to match it against our etc/ramfb that we're looking for. Once we find it, we have to read its selector. And what do we do with the selector? Well, we're going to write it back to the control. And essentially, we're accessing file 0x11. But now, instead of reading the data, we're going to write the data to configure ramfb. So what data do we write? We need to write all of this information. Specifically, we need to tell the GPU where the address to the frame buffer is going to be, what format we're going to be using, our BGRA, same as before. We're going to ignore the flags and go straight to the width. Here's the thing. Like I said, this is a very, very simple GPU. So can we even detect the screen size? Well, the answer is no. So we're just going to hard code it. And we're going to do the same thing for height. And then there's stride. Stride is just the bytes per pixel multiplied by the width. And the bytes per pixel is simply how much data each pixel takes up. Now, 1 byte is 8 bits, and we've already declared 4 different color channels at 1 byte each, so essentially 4 bytes. This just indicates how much space a single line of our screen takes up in memory. Great, so now we're ready to actually address the device and draw stuff to the screen. We're going to start with a very simple function, clear. All it's going to do is just write a value to every single pixel of the frame buffer. And that way we're going to get a solid color on our screen. Now we can continue developing more functions, but before we do that, we're going to write a GPU agnostic graphics API. Here's the thing. Our redacted operative system needs to communicate with the GPU and its driver. But we would rather it didn't know which GPU and which driver it's communicating with, because if we have to support multiple GPUs and multiple drivers, then that just adds a lot of boilerplate code. So instead, it's much better for it to communicate with our GPU agnostic API, and it knows which GPU it's communicating to and just simply routes the commands to the correct GPU. Now, this would be fairly easy to implement if we were in C++. We would just write 2 different driver classes and just make them inherit from the same parent class. Then our operative system just addresses the parent class, and we automatically call the subclass for the correct GPU. The problem is, we're not in C++. We're in C. And all of that fancy inheritance stuff, we don't have any of that. So I decided to do what I called bootleg inheritance. Essentially, we're going to call some generic GPU functions, and they're going to be responsible for routing us to the correct functions for the right GPU. Now, this works fine now that we have really just one GPU, because we have 2 drivers, but only one of them works. But if we ever add more GPUs, yeah, it's going to get out of control fast. So eventually I went back and rewrote this whole thing in C++ with inheritance, but for the time being, this is how it was implemented. Great, so now we have bootleg inheritance and we have a GPU agnostic API. Now it's time to actually draw to the screen. Let's start with a single pixel. We're going to create this drawPixel function, and we're going to address it by the location in which the pixel is and the color that we're going to write to it. Essentially, if we want to write to x coordinate 1, y coordinate 0, then we're just going to go to our frame buffer, and we are going to draw that in the second position, index 1. And our pixel is going to appear on the screen. But what if instead we want to address the second row with y coordinate 1? Well, now we need to keep in mind the stride. Remember, this is the number of bytes per pixel multiplied by the width. Essentially, we're going to skip all the data that is for the first row and just write to the second one at index 1. And there we go. Now we have a pixel on the second row. So from that, we're actually able to start creating some more complex functions, such as one for drawing a line, or one for drawing a rectangle or an area, which is commonly called a rect in GPU code. But what about drawing text? Well, for drawing text, we're going to use something called an embedded bitmap font. Now, I don't know if this is actually what it's called. This is just the name that I'm using for it because I couldn't really find anything online about how these are supposed to be called, but we're going to be using a font called font 8x8. It's a font that's 8 pixels by 8 pixels. Yeah, I really need to stop stating the obvious here. The way that it works is something like this in our code. Essentially, we're going to have a character A made up of a bunch of zeros and ones that indicate where there is and isn't a pixel. If you squint really, really hard, you might be able to see the shape of an A here. But okay, how do we actually use it? When we need to write an A, we're just going to find the index for the A character. And then we're just going to read its data right in a pixel where we find a 1. And just like that, we have our A. So if we implement it in our code, now we get a very, very small text. But we can actually use a scale as a multiplier to then have bigger text. Great, so now we have a lot of amazing drawing functions. But before we can move on and actually do something with them, we're going to talk about some improvements and optimizations that I've made. The first one addresses the frame buffer sync problem. Essentially, we are writing to the frame buffer at the same time that the GPU is reading from it. This can be out of sync and essentially lead to flickering, which is probably not something that we want. To fix that, we're actually going to write to a back buffer that our OS is going to be writing to. And after we're done writing, we're going to copy that over to the frame buffer, at which point the GPU is just going to read it. And now we can render with no flickering. That's great, but this actually introduces another problem. I'll call it the memory write problem. The problem is, when we write just one pixel, we're actually copying that pixel, but also all the other ones at the same time, which is very inefficient. This is where rects come in. And again, rect is just short for rectangle, but it's just what we call them in GPU code. We're essentially indicating an area that we are changing. So now, when we change a pixel, we're just going to indicate that this pixel has been changed by setting its rect as dirty. And now we can just copy over the dirty rects, in this case just one, and we can avoid writing all those other ones that we don't really need. That will make our GPU code a lot faster. So great, so far this is what we have, but this isn't really an operative system, I think. So how about we just work on a console instead? So let's get rid of this for now. And what's a console without printf? Now, if you've written even just 2 lines of code, chances are one of those lines of code was a printf or some other kind of console log. So most likely you know what this is. But essentially, it's just something that we use to log to a console in order to keep track of what's happening in our system. But the F in it stands for format. We're going to be using format strings, something like this. Essentially, we write hello world with this thing right here. And this indicates that after the hello world comes a hexadecimal number, which we can find as one of the arguments here. Now, for the time being, our printf is actually just going to write to UART, and we can see it actually writes as hello world with our hexadecimal number right after it. And if we test this out in our running program, yeah, we actually get our hello world with the hexadecimal after it. But I'm kind of getting tired of seeing all my output in the terminal window. How about we just create a visual console and see it on the screen now that we have a GPU? For this, I've actually started using C++, finally. So the way that this is going to work essentially is we're just going to keep a buffer somewhere that keeps track of the last few logs that we have written, and then renders them to the screen. So if we write hello world, then we scan it, and that gets written to the screen. Now, there's just one problem. How do we know when something's been written to the console? We don't have a file system, so we can write a log somewhere that we can read. So what can we do instead? Well, we have one major problem to fix first. Our console is written in C++, and printf is written in C. It needs to be accessible from anywhere in the system, so it needs to be written in C. The reason for this is that C++ has absolutely no issues communicating with C, but C cannot communicate with C++. So we're going to write a bridging function, something that helps us go from C to C++. It's going to look a little something like this. We're going to create an instance of our kernel console somewhere, and then we're going to create all these helper functions such as put C to put a character, put S for a string, or clear to wipe the console clean, which are going to call our instance of console. Now, you may notice that X turns C, and this is mangling. It's a C++ thing that is probably outside of the scope of this video, and honestly, I have been considering actually either creating a compiler or, if a miracle happens, finding the code for the C++ compiler I wrote in college, so maybe I'll make a video about compilers and explain this a little bit more in depth there. But what you need to know right now is that our function kconsole put c actually gets written as something like this in C++. It's z15 kconsole put c. Z indicates the return type, which is nothing, void, and 15 indicates the number of characters. There should also be the argument, but we're kind of going to ignore that for now. Essentially, this is not the actual name of the function, and if we try to call the kconsole put c function from C, we're actually going to find that the function does not exist. So if we add extern c to it, we avoid mangling altogether, and our function name is now just kconsole put c. Okay, so back to our console. Now we have bridged printf and console, so if we join them together, we get a little print on screen. Right now we only get one print, selected and initialized GPU 2, which stands for RAM FB GPU, the second one, because obviously we're not going to be able to see a visual console before the GPU is initialized. And great, that's our console. And at this point, I actually moved on to other stuff when I was making the operative system, but we're actually just going to talk about some improvements that I made in the future because I kind of did not revisit the console after this. So right now we have our console writing our buffer to the screen. But what happens when we reach the end of the screen? What happens to the next log? Well, the obvious solution to this would be to just move everything up by one row and just write our log there. But this is actually very inefficient. Let's not do it this way. Instead, we're just going to keep an index. This index is going to indicate the next place where we're going to write to our log. And we are going to make it go all the way to the bottom and then scroll back up to the top. That way we make our buffer circular and infinite. Okay, but wait, once we reach the bottom and loop back up to the top, won't the next log be on the top of the screen instead of the bottom of the screen? Well, yeah, and to fix that, we're going to keep track of where the index is on the screen. And whenever we need to draw a log somewhere on the screen, we're going to keep track of where it is in relation to the index and use that to calculate where it should be in relation to the screen. I hope that was understandable because I honestly have a hard time explaining this part and even more so in a visual format, but hopefully you understand what I'm talking about. Essentially, we're making it circular and using the offset to calculate where it should be on the screen. The other major improvement that I made comes when you think of the fact that printf writes to the console. But every once in a while, the console could have problems, especially while I was developing. It often led to crashes or exceptions, as we call them at this point. And we need to know what exactly happened, so we need to log that somehow. And I think you can start to see the problem now. Yeah. So to fix this, what we're going to do is the first time it happens, we're just going to print, go to the console, and an exception is going to get triggered. We're going to print that exception, but this time we're going to call a function called disable visual, and this is going to prevent us from writing to the console again. This way we will prevent an infinite loop. This disable visual function is also going to come in handy once we have a proper UI. At first, when we boot, we're going to show our console to show useful information. If by any chance the system fails to boot, we can look at the console and see what happened. But if it boots correctly, we now should see a UI, and so the console should no longer appear. We can just call this disable visual function and we won't have to worry about that anymore. Great, now we have a visual console, and we've actually talked about a lot of stuff today. We've talked about emulators, we've talked about languages, we've talked about buses, we've talked about GPUs and their drivers, and all that just to render a silly little screen. But there's actually plenty of other stuff that we haven't mentioned and that is very, very important to OS development, such as exceptions, the MMU, and even interrupts. But all of that is for the next video.